All right. Welcome back, everyone. So I think we mentioned this last time, but just a reminder, office hours, especially office hours on Friday, is going to be now on Mondays. So tomorrow we will not have an office hours, and next office hours will be this coming Monday at noon. Okay, we also have assignment 6 already posted. Hopefully we will have a chance to talk a little bit about it at the end of the lecture. Any questions about the assignment that is due today or the previous lecture? And let me pull off my chat because I'm not seeing it. So see, I use GSL library for ODE in GSL driver. Sure. So the relative error, it means, so when any of these methods tries to look for a solution, it's going to be comparing to the previous iteration that they found the solution, right? So think about the root finding algorithms. I think we discussed those, right? So the root finding, you try to achieve the minimal point. So the idea here is kind of the same. Your goal is to try to find a solution and compare to a previous solution. And basically the algorithm will stop when the difference between the previous solution that found and the current solution is less than a particular value. So there are two different ways in which you can measure these differences: absolute values, that's the absolute error, or relative error, which is the absolute value divided by the change. So you are basically saying, okay, how much change my solution compared to the previous one relative to the previous one. So usually it's a good idea to set those to, I don't know, 10 to the minus 5, 10 to the minus 4. So you're saying something in an error of 1 in 1,000 or 10,000, something like that. No problem. Any other questions? Okay, so let me pull the slides for today, talking about differential equations. We are going to continue with differential equations. Let me share my screen. And the topic for today is going to be partial differential equations. So before the reading week, we talk about ordinary differential equations. We are going to, and we left aside partial differential equations, and that will be the topic for today. So we're going to be talking about how to solve numerically partial differential equations. You should be seeing my screen right now, the slides, hopefully. So for today, we're going to see how to approach solving partial differential equations in the computer, how to approach that. And for doing that, the trick is going to be separating the differential equation in two parts, the temporal part and the spatial part. And we're going to see how to deal with each of these parts separately. And of course, some of the techniques that we discussed earlier will come back here and help us with this goal. So one thing I would like to start by mentioning is that there are different approaches in how people solve numerically partial differential equations. And here is just a summary of the most or the best known ones. So we have finite difference, which is one of the most used ones. It's quite straightforward to implement. And the reason why I'm mentioning here is not just to recap on them, but also to emphasize what parts of what is going to come in the course, or we have seen already in the course, is going to be relevant to this method. So for instance, in finite differences, matrix representation, and this is what we are going to be seeing today in particular, or what is also known as the stencil, is quite relevant. So it's at the heart of how one will implement a finite difference method. Of course, this, as we saw in the ordinary differential equations, requires some stability analysis of the numerical solution provided by this matrix representation. So topics like stability analysis are quite important. Identifying eigenvalues that can drive you the dynamic of the system are also important. And these topics, in a way, are recap or include in the linear algebra part of the course, which is going to be our next class. So next Tuesday, we're going to be talking about numerical linear algebra, and so some of the things will come back then. Another method, very powerful method, I will say, for solving differential equations is the spectral methods, or are the spectral methods. And when talking about spectral methods, we're basically talking about the composition in a particular set of functions of a given solution. And the paradigmatic example you can think of is Fourier transform or fast Fourier transform. So these spectral methods, you can relate to that. Now, we are going to be talking about implicit methods today, and the point of interaction with some of the topics that we have discussed is root finding. So basically, when you have an implicit method in place, you will be using some sort of root finding algorithm for helping these implicit methods. And again, this is going to be a little bit more clear later today. Finally, integration is practically something that is always part of differential equations. So things like random numbers and Monte Carlo are good tools when implementing integration methods. In addition to that, I'm not going to be talking about this in the course, that this why it's not color. There are special functions, special techniques that you can use with special functions, like integrating using green functions or potentials, these kind of things. Okay, but this is just kind of a quick, broad overview of the different approaches that people use for dealing with partial differential equations numerically. So as usual, please do let me know if you guys have any questions, if anything needs to be clarified. So let's start by reviewing our old friend, the partial differential equation, and we're going to focus just in a second order differential equation, meaning that the higher derivative that you will find in this equation is a second order. The quantity that we are interested in is this scalar field phi, or it can be a function, however you want to think about it. And there are some constants, capital A, capital B, and capital C. These are all constants in the problem. And what you can see, the main difference that you will notice with the ordinary differential equations is now this function phi will depend on variables x, y, and it could be z and w and many others. But let's just take for the sake of concreteness, saying depends on x and y. So now our differential equation, because it's up to second order, can be shown as a term with a second derivative in x, a second derivative in components x and y, and then a second derivative in y. Of course, you can have linear terms as well, and so on. But as I say, those linear terms can be represented by a dependency on the function of the proper second order term of the differential equation, being a function, a generic function g of x, y, the function itself, and the first derivatives of the function itself. So this is one of the most general ways in which you can represent, you can generalize a second order differential equation, okay? You will see, and you probably are familiar, PDEs appear all the time in physical systems, chemical systems, all kind of scientific fields will have or can be studied using partial differential equations. Now, something interesting as well of writing this equation in this way, and we're not going to go into details because it probably take us a couple of lectures to do so, is that depending on the values of the parameters of the constants in front of these terms, one can qualify or identify the type of differential equation we're dealing with. So, and this doesn't, I mean, it resembles a straight way, in a straight manner, the discriminant of a second order of a quadratic equation. Sorry, it's b squared minus 4ac, which b, a, and c are the terms, the constant terms in front of each of the derivatives. What happened here is, if we look at this quantity, and we see that if we see the quantity being smaller than 0, meaning a negative value, the differential equation is called elliptic. And an example of this equation is the Laplace or Poisson equations. If the determinant is equal to 0, if the combination of these four constants is equal to 0, the equation, the PDE, is called parabolic. examples of these are the diffusion equation or fluid equations described by Navier-Stokes. If the quantity is greater than 0, it's a positive value, still positive value, the equation is known as hyperbolic. And an example of this equation is the wave equation. So you can see by varying these values, we can change several things. We can change the type of equation we're dealing with, but also the nature of the equation, what is meaning, what is representing. So in the first case, you can think about a source in a differential equation. It can be like the Maxwell equations. In the last case, it can be just the propagation. So, depending on the particularities of the nature of the equation, what is relevant for the numerical techniques is that this behaves differently, and the approaches and techniques that one needs to be used or to use to solve them may change. One thing that must be said, and I think it's a topic that we have recurrently come during the course, is there is a package, a library, I should say, that can solve partial differential equations explicitly in your field, then explore using them, because differential equations and many other problems in physics or in numerics in particular may have annoyances that can be tricky to deal with, and people have developed some know-how in how to do that, especially in each niche, in each field. So why not taking a look at something is well known by doing that? That's not the approach we're going to take today. We're going to dive into a generic equation and see how to solve it. But again, a word of warning or recommendation, it will be, if there are packages, again, or libraries that your community is using for dealing with the differential equations that represents the particular problem you're trying to solve, and they are well known and used in the community, why not taking a look at it? So we're going to try to simplify, as usual, the problem just to see how to implement the solution, but that is not the most general case. Let's consider the case of a parabolic equation. And what you will see is then the only term I'm going to keep from this generic expression is the second order term in the x variable, and then a dependency on the time. So here it's going to be just the evolution of field T is going to represent the temperature, for instance, and then it's going to be a one-dimensional problem. That's why I only keep in the x variable. So we can think about the temperature profile in a road, for instance, very typical example and problem in physics. So this is nothing else than the heat equation. So it's a diffusive equation. And then the time evolution of the temperature is going to be given by the thermal diffusivity or thermal constant of the material, and then the gradient in one dimension of the temperature. So the question is how we can solve this equation. Well, in numerics, at least, one of the simplest way is to discretize both the left and right-hand side, meaning the space and time dependencies of the equation, and then just evolve forward in time the initial conditions that we have. So this is not different at all from the initial value problem that we have for the ordinary differential equations. The only difference, if you wish, is that we have an additional derivative to deal with, an additional derivative in an independent variable to deal with. So we have x and t in this case. So just a recap, a little bit of a recap, and just we're going to use the separation of variables. So let's consider, and again, I'm going to just focus on this equation right now. So t dots equal the second derivative of t with respect to x. So that's what we have here. What I'm going to say is, okay, let's consider that the second derivative, the gradient, the second derivative of the temperature can be written as an operator f acting on the function t, okay? And that is what I'm doing here. So, and I'm going to forget a little bit about this right-hand side of the equation, and then discretize my left-hand side. So if you remember, one way to discretize this was to use forward Euler, right? That's what we discussed in the ODE class. And so the derivative of t with respect to time can be written as the temperature at the next time step. So I plus 1 here represents my next time step, minus the temperature at the given time step, divided by the delta t between the time steps. And in this way, and if I apply this function here, if I consider the function, this operator f, applying to the temperature T at the given time step, then I can basically just do a little bit of algebra and then get my next value of the temperature at the next time step just by multiplying delta T here and moving T sub I to the next side. Now, one thing that one must be careful, and in order to generalize this to higher dimension, is you may need to think of f being an operator acting on a matricial way. So meaning f can be thought or think as a matrix. So in this way, T will be a vector of temperatures for different time steps, and f will be the matrix acting on that. The reason why I'm saying that is because usually when you deal with matrices, the order matters when you are multiplying. And that's why I have here, I'm going to try to preserve the order of multiplications of these factors. It doesn't matter in the scalar case where we have only x, but it will matter in the future, okay? Now, this is using, as I was saying before, a forward Euler. And one thing that you can very clearly see from this equation is this is what we usually refer as an explicit equation, in the sense that I can explicitly see the dependence on time. Remember, the I variables subindex here represents the evolution in time. I can see how the next value of the temperature in time steps is given by the previous one. Now, if you remember for our ODE class, we saw that forward Euler may have some complications in terms of stability. So what happens if we decide to use, instead of forward Euler, we decide to use backward Euler? So my discretization will be kind of the same. I can represent this as the same. And what backward Euler will tell me is that the right-hand side, instead of being f of t I, it will be f times t of I plus 1. Or I can just swipe indices here. I can put here I and I minus 1, and then this will be the same thing, and then move everything to I plus 1. Bottom line is that if we write the backward Euler discretization scheme for this equation, what we can see, if I want to get t of I plus 1 or t sub I, however you want to write it, now the dependency is this operator 1 minus delta t times f multiplying the solution and after is equal to t sub I. So this is what we know, or what we call an implicit method, because for getting the t sub I plus 1, excuse me, I have dependencies on the left-hand side. So these two different approaches, implementing a forward Euler or a backward Euler, leads to different implementations in how we are going to be solving for t sub I plus 1. And again, bear in mind, this is going to be given in a matricial way, and that's why it's not so easy to just put this thing divided on the other side. Okay, so we will need to invert this matrix, and there will be dependencies acting on t sub I plus 1. So that's why it's not so straightforward to just get t sub I plus 1 from there. Now, let's talk a little bit about the explicit methods. I think I mentioned this, but the explicit methods are referred to when only t sub I is on the right-hand side of the equation, like on this case, for instance. They are easy to implement because they are kind of straightforward. You just evaluate and boom. So they are easy to implement and quickly to calculate because there is no matrix inversion whatsoever. Because of that, they are also easy to parallelize. So if you're thinking about parallelizing this algorithm, they are basically easy. They are inherently local, so no worries about that. There exists more accurate explicit method than forward Euler. We saw this also in the ODEs. We saw Runge-Kutta, for example. So, but in general, you can think about the explicit method in this kind of prescription. The next time step is given by a combination of operators applied to the current time step. But there are also some downsides, as we saw in the ODEs. They are not very accurate at low orders. So the order here in forward Euler is of the order delta t. So if we want to have something more accurate, we will need a higher order expansion of the derivative, and that will make things a little bit more complicated. And also something that we saw, I hope you guys remember from our ODE lectures, is that they can be numerically unstable. though there are some exceptions, but in general, they can lead to numerical instabilities, okay? So this is a little bit about explicit methods. About the implicit method, basically they are implicit when t sub I plus 1 is in both sides of the equations. And again, just to recap. So by the way, this is the expression at first order in delta t. And this is what you will have a second order in delta t. Okay, so this is the example with the back-over Euler that we just worked. This Crank-Nicholson is when you go a little bit higher up to second order in delta t. And basically what you are doing is here approximating. You can think about this as approximating the derivative of t, of the temperature as a function of time, as the middle point between the next time step and the previous time step. That's basically what you're doing, or taking a second order approach in a second order accuracy term in the Taylor expansion. So the implicit time stepping method has some nice features. They are way more stable than the counterpart in the explicit side. So it takes over a wide range of time step size. Sometimes they are even unconditionally stable, not unconditionally accurate though, but unconditionally stable. It means for whatever value of the delta t they will be stable. They are really good for solving. This is important because it depends again on what type of problem you are trying to look at, for solving steady state solutions. So the transitory will quite probably be not accurate enough, but after you reach the steady state solution, then that is going to be a very robust solution. The downsides, of course, as you can see right away from the equation, is they're a little bit more difficult to implement and way more difficult to parallelize. And the reason is inverting the operator that depends upon all the grid points. And we haven't talked about yet the spatial part, but this operator F carries on dependencies on the spatial derivatives and the spatial points in the grid. So that is the tricky part with the implicit methods. Okay, so what we have seen so far is two different ways of tackling the temporal part of the differential equation: explicit or implicit method related to how you discretize the derivative, how you approximate the derivatives, right? And both sides has advantages and disadvantages. One thing I would like to mention, this is not in the slides, by the way, but one thing that people have noticed sometimes is, you know, the truth doesn't lie in one side, in either side of the coin, is a combination of implicit and explicit methods, sometimes called IMEX for implicit explicit, can be a good trade-off. This is particularly true, for instance, when you're dealing with electromagnetic fields and there is a dynamical situation going on, like the electromagnetic fields can be changing rapidly. So for reaching a good stable solution in the steady part, but also capturing the features of the transitory under certain conditions, the combination of implicit explicit method can be a good thing to try. Just a parenthesis issue here. Any questions so far? All right. So we have seen a quick overview of how to deal with the temporal part. Let's take a look at how to deal with the space part. How we can discretize the spatial part of the equation. So there are many different approaches that one can take for dealing with these fields in the spatial part: finite difference methods, finite volume methods, finite element methods, and spectral methods. So I talk a little bit about the spectral methods. The finite difference method is nothing else than dealing with the derivatives in a discretized manner and defining what we call the stencil of the operator that tells you how to discretize, how you can approximate the derivatives. Now, what finite volumes and finite elements, and I have a couple of slides at the end. I don't know if we will have enough time to cover them, but they are included there for you if you want to look at them, especially if you have to use it in your field. Finite volume methods tries to discretize the volume itself, and finite elements methods try to use elements instead of the single points in a grid. So these are the similar ideas, but different approaches at the end of how you implement that. Of course, one can use a combination of this, and this has been proved to be very, very powerful in the same way that the implicit combination of methods. Many people use finite difference combined with spectral methods. Spectral methods are very well known to be very, very accurate, probably among the most accurate methods. They are quite expensive at the beginning to identify which is the right expansion of basis of functions for your problem. But after you have identified those, they are super easy, well, not super easy to implement, but super fast to compute, because you basically are going to be evaluating functions. And because of that, they can also reach very high accuracies if you have a really good expansion. So sometimes you will find yourself combining different approaches, and that's a good idea to have an overview of all of them if you can. So again, we're going to be focusing on the final different methods for the spatial part as well here, because they are the simplest way to deal with the equation. The main idea is that our simulation domain now, not only in the time evolution, but also in the spatial discretization of the grid, in this case, in the spatial points on the rods, are going to be discrete. And the derivatives are going to be approximated by linear combinations of the functions at the grid points. What we're going to use in this particular case for the second derivative is to use what we call central differences. And this you can basically derive by using the same approach as we did with the Taylor expansion for the first order derivative and then apply to the second order derivative. But basically what you end up having is the temperature evaluated at different points. And now here the sub-index shade represents the spatial points on the grid. So I'm going to keep this convention of I, the sub-index I, to represent the different time steps, the evolution in time, and shade will representing the spatial points on the rod or on the grid in general. So my second derivative here for the temperature in a given point shade on the grid is going to be the temperature on the next point on the grid minus 2 times the temperature on the actual point plus the temperature on the previous point divided by the spacing on the grid, meaning how much the spatial difference between the points on the grid. There are several assumptions here. I'm going to assume the grid is uniform and it's a regular grid. Okay, and this works, as you can see, for Cartesian coordinates. If you are going to move into a cylindrical coordinates or polar coordinates, some of these expressions will change. Okay, similarly, if the grid is not uniform, that's also a usual thing that people had to deal with when you need to have more accuracy for a particular part of the grid, because the example I always use is the simulation of binary black holes or neutron stars close to the center of the merger or the system. Then you need to have more resolution because it's where all the dynamics happen, right? But you can think about different examples where this may be true as well. So how we compute these derivatives? This is just a recap of how you will do it, how you will obtain this expression, just to convince you yourself. This line on black here represents the grid. This is the point where I'm stepping at shade. Shade minus 1 is the previous, shade minus 2 is the previous to that one, shade plus 1 and shade plus 2. So if I want the function f at the point shade minus 1, then I can use the Taylor expansion to say, okay, f of x shade, and basically the way that this works is you evaluate f of x shade at f of x shade minus 1, you multiply the first derivative of that by the delta x, and so on with the second derivative. F of x shade is just f of x shade, and then f of x shade plus 1 is the Taylor expansion at the point f of x shade plus 1. So it's a little bit of algebra. The only thing to bear in mind is here, because the delta x goes to the left, it's a minus delta x here, the delta x goes to the right, it's a plus delta x here. In the second term, these contributions don't matter, because 2 steps to the right or 2 steps to the left, because the square factor on the Taylor expansion makes a positive contribution. And you go up to the third order, that's the order, the error in the expansion. Now, if we come back to our previous point, you will see these terms will appear here. So the temperature of shade plus 1, the temperature of shade minus 1. So now I want to combine all these, combine the information of and f here can be just any quantity, but let's recap to the temperature. if I want to combine this to just write this in a very concrete manner, what I can use is a matrix notation. So I'm going to combine these three elements: the function at the point on the left, the function at the center point, and the function at the point on the right. So this is going to be a vector. And so I can rewrite now this as a matrix multiplication between this matrix and the vector of the derivatives. So let's just look at the first. So the second one is kind of trivial, because I just get 1, 0, 0 multiplied by f prime, and f second. F prime and f seconds are the spatial derivatives of the function. So I only get the f. For the first one, I get f minus delta x times f prime plus delta x squared over 2 times f second. And that's exactly what you have here. Okay, so I invite you to convince yourself that this matrix represents and allow you to actually obtain these equations that we just derived here. I see your question, Rob. I take it in a second. Let me just finish this slide so I don't lose the continuity on that. Now, one thing we can do is we can invert this matrix. You can prove this matrix is invertible, and you can quite easily invert the matrix. And again, I invite you to convince yourself to multiply these two matrices and get the identity that we can then obtain expressions for f prime and f second. And just by doing so, then we can say, okay, f of xj is going to be fj, easy peasy, f prime this quantity, and f second this quantity. So now we end up with expressions, explicit expressions for the first derivative and second derivative based only on the values of f evaluated in the points on the grid. And this is quite useful indeed. Okay, so let me take Rob's question. So, oh, sorry. So this diagram here, oh, I'm so sorry about that.
So I can barely see it.
Okay, even if you don't look. So one thing that can help with that, let me see if I can pull this. So usually in the website, I put it's there, but I can't see here. But on the website, let's see. Sorry, I may need to stop the share here for a second. Let me see. On the website, I put one version of the slides. That is the handout version, and that version is on white. Let me see if we can pull that one. Maybe we can continue with that one. I apologize because of that. Share screen.
It might be just the contrast on my screen.
Yeah, no, that's fine. That's fine. So let me go all the way. So these are with white background. So I think it should be easy to see. So this is the diagram that I was talking about. So we have Xi as the central point. This is the diagram you were talking about, right? So we have Xi at the center of the grid. Then Xi minus 1 is the point on the left, the first point on the left. Xi minus 2 is the second point at the left of Xi. And then Xi plus 1, the next point to the right. Xi plus 2, second next point to the right. Make sense now? I hope it makes sense.
Sorry, it makes sense now. I couldn't see it before.
No, so that's fine. That's fine. Again, I apologize because of that. Maybe we can continue just with the slides with white on the background. We used to have the slides on black because when we teach this online, in person, we have a huge screen that if I put the white background, it will just burn your eyes. And, literally. And then we switch to the black background. And I think we keep it because we thought, okay, it's kind of stylish, but I can see that in some diagrams we need more contrast. So no, that's perfectly fine.
I appreciate that.
I'm sorry about that.
Thanks.
But I hope that kind of I have convinced you at least that we have an expression for our first and second derivatives of whatever function we want to represent. In this case, again, coming back to the example of the temperature profile on the road, given by just evaluating the function at the different points on the road, basically on the grid. So let's put all this back together. So we get an expression that depends only on evaluating the function at the same point in time in different points, different spatial points on the grid. That's what we have done just right now. Let's put all this together. So we started with this equation, the heat equation, and now we're going to write the equation in terms of its discrete parts. And as I was saying, I will represent the temporal part of the temperature, and J will represent the spatial part of the temperature. Meaning, if I have I in both sides, it's at the same time step. If I have J at both sides, it's the same time point in the spatial grid. If I have J minus one, it's the previous one on the left, J plus one, the next one on the right, and so on. So one way I can rewrite this equation, the first order time derivative of Tij is then having my conductivity constant multiplied by Tij plus 1 minus 2 Tij plus Tij minus 1 divided by the space, the gridding space in the rod. And this comes nothing else than from this last equation here. Okay, we are not using the first derivative. This is because the simplicity of the stencil of the implementation I have decided to use for my second derivative of the temperature, but other methods that use higher order derivatives may need the first derivative as well. Okay, that's why it's need to have it. But as you can see, it can be in a similar fashion expressed in that way. So how we deal with that now? So this is our equation. Our equation has gone through the continuous description of the problem to a discrete description of the problem. This, by the way, is an interesting problem in physics. Even on classical mechanics, this can be an interesting problem, because if you have the situation where your system has constraints, and coming back to the example of the rod, maybe you have a source of heat or something that keeps one of the edges of the rod at a fixed temperature, then this is a constrained system. There is an external agent performing work on the system, and one has to be careful sometimes in the discretization approach that you're going to use. So there's a lot of work done on that regards, and I can tell you just that it's not trivial to deal with those systems. So just another word of warning. As you can see, there are a lot of details that usually we skip or are not present when discretizing things, but sometimes it blow up in our face if we don't recall them or consider them. All right, so I hope that you guys are okay with this shape or this form that the equation has taken. It's the discrete form of the equation. Now, what I'm going to do is try to represent this again in a matricial way, and you're going to see why this can be useful at the end. Basically, all our mathematics are going to end up being matrix vector multiplications, and this is kind of neat because there is a lot of good libraries that can help us to implement that in just one line, and that is the code I'm going to show you at the end, how to solve this equation basically just with one line of code. So what I'm going to propose now is to take the temperature function, which depends on the temporal part and the spatial part, so two components, and represent this temperature as a vector. Now, this vector, what it will be is just the vector for a given moment in time. So I here again is going to be my temporal index. So I'm going to have a vector, basically each point of the rod is going to be represented in this vector at a given moment in time, at the time I. So if I consider that vector, then I can say, okay, the time derivative of that vector is equal to the conductivity constant. And then what I had to do is generalize this expression for this vector of spatial points. And how can I do that? Well, I'm going to invite you to show or demonstrate that this can be generalized with a matrix that is what we refer as a three-diagonal matrix. So it has a diagonal, and it has the upper and lower diagonals, and then the rest of the matrix is full of zeros. And again, this has very nice properties from many aspects. So let's take just the line 19. So for the point 19, this is the time derivative of T19. So K multiplied by this vector again can be seen as the only element that will survive is the previous to the diagonal the diagonal and the next one, and this is 18, 19, and 20. And if you put those values here, you will see that you can recover this expression. Okay. Again, I invite you to do this algebraic exercise, but basically one can summarize this expression as this. So this formula can be given as the derivative of this vector at the moment in time equal an operator. F is going to be this matrix now multiplied by the vector at the moment in time, I. And that is a very neat, a very elegant way to summarize this system. So one thing that you may notice is what happened with the edges, what happened at the beginning and at the end of the road, right? This is the TI0 and TI100 for saying that there are 100 points. So what happened with that? Well, for dealing with that, we need to look at the expression of the equation, and you will see that in that case is if I put j equals 0 here, I had a 1, I had a 0, but then I had a -1 here. And there is no point -1. So basically, the solution is not to use this equation. This equation is valid for the inner points, but not for the edges. And so we will need to use a different equation to describe the edges of the road. This is where the boundary conditions come into place. And one of the differences I should have mentioned at the very beginning between ODEs and PDEs is that in PDEs, you not only have the initial conditions, but you also have the boundary conditions, because there is a one extra dimension, thinking about one-dimensional problem, that describes how the fields were originally set in the space, not only in the time. So there are usually two ways and combination of this that you can use. You can use a Dirichlet boundary condition that is a constant value, or you can use a von Neumann boundary condition, where basically you set the derivatives of the boundaries for that. How these conditions are implemented depends on the approach to solving the equation itself. Okay, so I'm going to show you a particular one in this case. Let's suppose, but again, this depends on the physical problem itself, right? We cannot say anything in general unless we have the boundary conditions as well as the initial conditions. So let's suppose that we have a rod, as we were saying, the length of the rod is 1, and then the temperature T of function of T and X is subject to the boundary conditions that is going to be for the initial point, the beginning of the rod, it will be the sine of 10T. It's going to be a forced change in the temperature. So it could have a heater oscillating between values of the temperature as a function of time. And then at the extreme is going to be 0. So we're going to assume that by the end of the rod, all the heat, all the temperature is dissipated. Thermal diffusivity or thermal constant is 0.2, and that we are going to assume that we're going to discretize the rod with 100 points. So these are all parameters for how we're going to implement this. How we can solve the problem, as we discussed, we can use an explicit or implicit method. Explicit methods are known for its simplicity, and that's the path I'm going to follow in what is left for the lecture today. So this is just a little bit of a recap of what we discussed earlier, but now applied to our vectorial form of the temperature profile. So it's the same idea as before. I'm going to take my first order derivative in time, discretize, equal to the operator on the right-hand side applied to I+1, because I'm using the explicit approach. And then if I do that, I just do a little bit of linear algebra to move things one side or other side, and then I end up with this final expression. And this is a super neat, super concrete, closed form expression. You couldn't ask for anything else here than having the temperature profiles on the rod at the next step equal to a matrix multiplication operation on the right-hand side. That's as easy as it could get. And by the way, the one here, because as you notice by now, F is a matrix, we are dealing with the identity matrix here. So 1 represents the identity matrix. So this is the matrix, the identity matrix plus the operator F that we discussed before, the 3 diagonal matrix multiplied by the delta T, that's the time step, and the previous snapshot of temperatures on the rod. That's basically what it is. Okay. So with that in mind, putting everything back together, so this is the equation that we're going to implement now, we need to also set the initial conditions, or the boundary conditions, I should say. So for j equals 0, our first point on the road, basically what we are saying is the temperature at any given time, I plus 1, at element 0, the first element on the road, is sine of 10 times the value of the time. And that is what we have here. So you can convince yourself again by putting all these zeros. You kill any other contribution for any other points on the road, and you only keep the temporal excitation on the first point on the road. Now, the other thing I have done as well is to simplify a little bit the expression of the matrix by defining this alpha parameter. And this is nothing else than delta t times the conductivity constant divided by delta x squared. Okay, so you can again convince yourself that that will reproduce the expression we had for the matrix before. There is one more boundary point that we need to deal with. That is at the other extreme of the road. And again, I'm going to play the same trick, fill with zeros this row, so it kills any other contributions from the road, and this one put in 1, because the last point has a temperature of 0, is fixed at 0. That's what my initial condition, my boundary condition says. Then I'm going to put just a 1 here for simplicity, but I could put anything else because multiplied by this 0 will kill any contribution. Okay. Any questions about this? So sort of we had converted our problem of the differential equation into, I don't know if you realize about this, but just a pure exercise of matrix vector multiplications. That is what we have done so far. And that is one of the most beautiful things I can ever found in computational methods, translating that problem into just a matrix vector multiplication problem. Now, please do let me know if there are any questions. There are many details and caveats here. And again, many of them are swept under the rug here. So feel free to ask if something is not clear. But in the meanwhile, let me show you an example of how this can be implemented in a code. So for doing that, I'm going to just use mathematical tools and then C++. So that's a library we're going to discuss more in detail next class. This is my main function. It's a monolithic implementation, not nice, but straight to the point. So I define a couple of constants or parameters here, the conductivity constants, for how long I want to run, the number of points on the grid. Then I'm going to define the delta x as the length of the grid 1 minus divided by the number of points minus 1. Then my delta t is going to be 5 times 10 to the minus 4. The number of steps is nothing else than the runtime divided by the delta t. And then some parameters a and b for the equation. Then the alpha, as we saw before in the definition for creating the matrix, is delta t times kappa divided by delta x squared. And then we're going to define some arrays for putting the temperature profile, the right-hand side, and the matrix operator. Okay, so that's why there is a double star here, is a pointer to a two-dimensional array. I'm going to initialize first this with allocating enough space for the whole array, and then initialize. So these 4 loops that you see here, there is one here, one here, and then 2 more nested here, are for initializing the different elements on the matrix. So you may recall this matrix has a particular shape, is a tri-diagonal matrix. So we only need the diagonal, and we only need upper and lower diagonal. So the matrix is going to be initialized at 0. Temperature is going to be initialized at 0 originally, and right-hand side the same. And then I'm going to take a special care of the different parts of the matrix. All this to say that this for loop, and this third for loop are just to create the matrix and the vectors, and that's it. The last for loop, this very last for loop, is the one that actually does the time evolution of the system. And let's take a look at that. So I'm going to create a temporal array just to pivot the right-hand side of the equation. So initially, my right-hand side is t, and t is going to be assigned the temporal pivot there. So I'm going to set the initial condition to be the boundary condition, sorry, at the origin to be this sinusoidal function as we described before. And then the right-hand side of the last point equal to 0. That's the other extreme of the rod. And this is the routine. I promise you this. The whole system is solved in one line. So this is the routine that does the vector matrix multiplication. It's a call to the cblast function, to the cblast library. The function itself is called cblast underscore dgmeb. The name is very cryptic. We are going to dive into this next week. But basically what it's doing is multiplying a matrix with a vector. These are some flags. Again, we're going to look at them more in detail next week. These are some parameters, but basically this is the vector that is multiplying. It's the vector t with the right-hand side. Okay, so this whole call in dark red, if you wish, it's just one line. Well, all what it's doing is multiplying the matrix, the operator, the stencil of the system times the temperature vector, and that's basically it. What is left is we need to output the results, we need to deallocate the memory that we allocated, and that is it. So I just put comments here, but that is what you will do. Usually you say your results and so on. So this is how it looks like. So if we run this, I set the value of alpha or the computation of alpha is equal to 1. So this is time and this is distance. So this is a little bit rotated, but this is the time evolution and the distance. What you see is this is a profile. So this is the solution. Something is not quite right because basically the solution died very quickly. And a way to see this more in detail is to see different time slices. So this is the temperature now on the vertical axis. This is the distance. So this is basically the rod, the first 20% of the rod, if you wish, at time 0. And okay, this is not showing up nicely in this slide, but basically you will start to see oscillations and then this blowing up at some point here. I invite you to see that in the other set of slides. But yes, the allocation of the memory in this case, in how I implemented this, it has to be done because I did this by hand. If you are using auto-race, then that's just fine. I usually personally like to deallocate the memory. I feel it's all style. But if you're using automatic arrays, you may not need to do that. Okay. It's a good question, though. So what you will see is that this solution for the temperature, and again, I invite you to see the dark slides because if for some reason the handouts slides break this animation, it will blow up at some point. So the question is why? What did go wrong here? So let's try to take a look at a smaller system here. So just 5 points on the rod. And one thing that I told you a little bit about this, it was a very, very quick mention at the beginning. This is nothing else than a linear system in the matrix world. And one thing that matrices are well known for representing in dynamic systems is they can tell you about the stability of the system. So if we do the exercise of computing the eigenvalue of this matrix that governs the behavior, the dynamics of the system, what you will see is, well, this eigenvalue is easy to compute because it's a sort of diagonal matrix, will depend on alpha. And one of the criteria that we have for stability on the system is the same criteria that we discussed last time we saw the is the largest eigenvalue of the system has to be in absolute value smaller or equal to 1, which ends up imposing a constraint on the parameter alpha that we have here in the function. With this imposes basically a constraint of saying alpha has to be smaller or equal to 0.5. Basically, it's telling you that the time step in which we evolve the system to have a stable evolution has to be smaller than the square of the discretization in space divided by 2 times the conductivity constant. This resembles nothing else than the current factor stability criteria, and it's something that is well known. You can see this in different ways. You can see how fast the information is propagating on the grid and violations of certain criteria. So, or you can see it as a stability criteria for this particular linear system. So basically, if you double the spatial resolution, you need to quadruple the temporal resolution to preserve stability on the system. In other words, if if we change the value, so I was using a parameter alpha equal to 1. If we change the value to 0.1, now you can see a very nice evolution in time of the temperature profile on the rod, how it's propagating and dissipating very quickly, because we put a sink of temperature basically in the other extreme of the rod, and you can see the temperature profile basically propagating and dissipating. Okay. So we need to pick a proper value of alpha. That's the bottom line, the end of the measures here. Just a few things about the implementation, and unfortunately, as I was telling you at the beginning, we won't have time to discuss the other methods, but the material is there in case that you're interested in looking at it. The code allocates and fills the entire matrix, but most of the matrix is zeros. You can see that. I have another slide here. You can see that the basically gray portion, almost 90–80% of the matrix is zero. This is what is called as a sparse matrix. So there is a more efficient way to say this matrix and operate with this matrix, and we're going to see this in next class as well. This is a good way for implementing things initially, testing, but also understanding how they work, but not a good way to do production. And because basically this matrix is banded, and if you increase very largely the number of points and the spatial resolution, this matrix will grow very quickly. So it's not quite efficient. Banded matrices, which allow you to store just the information of the diagonals, the elements that are not nil, are way faster, use much less memory. So that's the way to go. The downside is that the banded matrices are a little bit more complicated to store. So you need a little bit of implementation details there instead of the full matrix. So this is what I'm talking about by banded matrices. So you will store the diagonal, the upper diagonal and lower diagonal, and you can see the rest of the matrix is zero. So instead of storing n by n square array, you will store just a 3n square, and it's substantially small. You can see how that propagates if you increase n as well. What is left, and we're going to come back to these banded matrices on next class, because there are routines that are especially designed for dealing with banded matrices in the linear algebra libraries. What is left of these are a very short review of the finite volume methods, the continuity equation, which is very useful and very neat to see with finite volume methods, and some of the details of the finite volume methods and the spectral methods. Again, I invite you to go through the slides. We don't have enough time to see all that, but I wanted to include that just for completing it. So I think that is all what I have for you today. Again, if you are in a particular field that use spectral methods versus finite differences methods or volume methods or finite element methods, it may be worth taking a look at this. We can have a chat about that. But I think at least it's a good introduction of how you will implement a finite difference method from scratch for a differential equation, a partial differential equation, with all the simplifications that we have considered. Okay. Any questions about this? Oh, thank you. So I keep the chat open in case you guys have more questions. Let me see. Because we have the assignment posted already. Let me see if we can go quickly through the assignment. So this assignment, as we promised you last time, is going to be about reviewing the code that some of your peers have written for assignment 4 and implemented unit testing. So we are preparing the submission. So as we promised, they are going to be anonymized, and we are only going to give you the IO routines modules that you guys wrote. So you are going to do something like git clone. This is on the teach cluster, of course, git clone, and then submission, and you get a number. Okay. So you will be notified by email about that. And then after cloning, your task is quite fun, I hope, is to write a short code review. I would say a maximum of 3 pages. Don't go crazy on this. And it will address things like how is the code structures? Are there comments? Do we include documentations? How is the logic? Potential performance issues that you may see, readability and maintainability. Whether these functions could be used in your own code, and if not, why? techniques in the code that you like it and may use in your own code, something that you learn from the code, let's say, suggestions for improvement, but do not implement yourself, just a report, right? We have, Rancis created this nice recap of lessons learned from scientific software development, and it can give you a kind of idea of what we are after. So it's a fun text to read, and I hope you guys can see some of the things that we have been mentioning in the course reflect there. So that will be the first part, okay? General comments is try to keep your criticism constructive and try to strike a professional and collegial tone. Add the review that you have written to the repo, and it can be plain text, it can be Markdown, LaTeX, or PDF. Okay, try not to use any proprietary format for this. The second part is writing the unit test for these modules. And at least there should be one unit test for every function defined in the header file. So you will see some of the assignments has auxiliary functions, that's fine. But if those functions are not declared in the header file, then you can just omit, just write the testing functions for the ones declared in the interface of the module. For running the test, we would like you to use one of the frameworks. It can be Cat2, it can be Boost Test or Google Test. Boost Test is the one that we discussed in the lecture. All of these are installed in the cluster. You don't need to load the three together. You just pick the one that you want, so either Catch or Boost or Google Test, and that is it. I think Cat2 is the simplest one, although we didn't talk about it. Boost is a good one. I think many people use Boost in general in the professional software development discipline. So I would say Boost is a good compromise. And yeah, so the idea is to implement the unit test for all the functions defined in the IO model interface. One important thing, do not use the same data as the full Anson table code. Instead, use a simple, smaller version that is easy to read and write. The other thing we want is to use a make file and Git all through your assignment. So whatever changes you do, commit to the repository and create rules for running your test. So there should be one rule for target test. So if you have three functions defined in the declaration of the module, then there should be three new rules. And then we want to have an overall rule test for running all the tests, okay? The same comments as usual, several meaningful commits. Do not commit any data that is produced. Do not commit derivative stuff as usual. And make sure to commit all necessary files to run the code and its test, okay? Okay, the due date says Monday, March 4th, but it means Thursday. Yes, that's right. It's a Thursday. That's exactly right. Is it right? Yes, it's a Thursday. Yes, we will fix that. Thank you for noticing that, Michael. All right. And just to repeat myself, as I mentioned at the beginning, we are not having office hours on Fridays anymore. So next office hours will be on Monday at noon. All right. Any questions about the lecture today or the assignment? Let me see if I didn't miss any questions in the chat. I hope I did not. Yes, Lauren, go ahead. You can use a sparse matrix. One of the advantages of the banded representation over a space matrix is that usually I would say 99% of the stencil. So when I mention a stencil is a concrete technical jargon for saying the matrix that represents this PDE. 99% of the stencils for PDEs are banded matrices, meaning that it has a diagonal, it has two or more subdiagonals. So if you go higher in the order of the integration scheme, you will start to add more subdiagonals. So it's quite easy to represent those bounded matrices. And there are routines that can deal with that in the linear algebra libraries. Sparse matrices, you can store them, sure. The issue with the sparse matrices is it's a more generic way to storing the bounded matrix. So it has a little bit more of a structure to recognize on that. So you know, there are those things, but also there are not so many linear algebra specialized functions, I would say. So that is the downside of sparse matrices. You could, but maybe it's not so advantageous unless you really need to do a sparse matrix per se. Again, there are cases, there are problems and computational algorithms that need and use sparse matrices, but for PDE in particular, I will stick to bounded matrices instead. And again, checking that I didn't miss anything in the chat. All right. Okay, guys. So I think that then we are done for today. Yeah, reminder that due date for assignment is tonight, and we will see you next week then.